Good morning, gentlemen. Today we will start on screw propellers and we will start with geometry. Every ship has an engine which is connected to a propeller shaft, a sort of shafting system consisting of a number of units. Ultimately, at the aft end, the shaft is known as propeller shaft, to which is attached the propeller. This propeller is rotated by means of the moment or torque supplied by the engine at a particular RPM. So, once this propeller rotates, it moves in a hydrodynamic medium, and through interaction of water and the propeller blade, an axial force is generated, which is known as thrust in the direction in which the ship is moving. A ship, when it moves forward, it experiences resistance to its motion in the reverse direction. This force generated by the propeller, known as thrust, overcomes this resistance and allows the ship to move forward. This is the principle on which the propeller works. Simply said, or diagrammatically said, it is like this. You got the engine here somewhere. You got a shaft coming here, and then this comes out of the ship on which is housed a propeller. Now, the engine provides the moment to the propeller at a particular RPM. This propeller works in this fluid medium. This medium is fluid, water, and produces a thrust or an axial force in this direction, which is finally transmitted to the ship along the propeller shaft. And since the propeller shaft houses a bearing here, thrust bearing, through the thrust bearing it is transmitted to the ship structure, and the force is applied to the ship, and the ship moves forward, overcoming this force R, resistance, which is experienced by the ship at a particular speed v. The propeller geometry is such that when it rotates, the one side of the propeller forms more or less a part of a screw. I suppose all of you have seen a screw, a nut and bolt, a bolt on which a screw is carved out, and when you rotate a nut, it travels in a particular fashion. A propeller blade surface, one of the surfaces, is a part of this screw surface, and that is why a propeller fitted behind a ship is called a screw propeller. So, this is called a screw propeller. Before we go further, it is necessary for us to understand the geometry of a propeller. So, what have we got so far? The torque coming out from the engine being applied on the propeller is called torque Q, represented as capital Q, and its unit is Newton meter. We are all talking about SI units. Rotates, the propeller blade rotates at RPM at revolutions per second, denoted as small n, RPS, unit being second inverse, Sometimes it is more convenient to say revolutions per minute, in which case you write capital N RPM, which is equal to n into 60, right. And then we have thrust generated, which is called thrust, and the unit is that of force, newtons, and this operates at a speed normally called velocity of advance, VA. Now, this velocity of advance varies as where the propeller is working. If the propeller is working in open water, which we will be seeing, the VA will be equal to the speed of water, whereas if it is working behind the ship, it will also, the VA will be the mean velocity of water onto the propeller, which may be less than the ship speed. That is, if I write Vs as ship speed, VA will be less than Vs. Units of all speeds will of course be meters per second, or more conventionally knots, which can be converted to meters per second by multiplying with 0.5144. I have got some propeller to show you here. I think I will show you this propeller. This is, can you see this? This is a model propeller having 3 blades. Can you see this? This portion is called the boss of the propeller, on which there are 3 blades. Okay. So, this is a 3-bladed propeller, and this boss as a whole, as you can see, which sits on the propeller shaft like this. So, the shaft is on my right and the ship is also on my right. That means this side is the aft side, or this portion is behind the ship. The ship is in front and it is moving that way. How is the propeller rotating? This is, if you are looking from behind the propeller, behind the ship, let me say, still we have not said which is front and back of the propeller. Suppose I am looking at the propeller from behind the ship, okay, that is from this side. Then if it rotates in the clockwise direction, is it the clockwise direction? This direction? Anti-clockwise, okay. So, how will it be clockwise? How will it be clockwise here? This way? Right. If it rotates looking from aft, that is this side. If I rotate it like this, then this is clockwise, this is called the right hand screw, right handed screw. If it rotates the other way, then it would be called the left handed screw. Now, normally single screw propellers are all right handed propellers, right hand screws. But if I have a twin screw propeller, that is one on the port side and one on the starboard side, to balance the uneven forces that may be generated, I would like to rotate the propellers, each propeller in the opposite direction. So, that means one will be right handed propeller and the other will be left handed propeller. But right now let us look at this right handed propeller. What are its characteristics? The side that is facing you when you are standing behind the ship and propeller, that is this side, is called the face of the propeller. This is the face, and actually it is behind on the aft side, and this is the back of the propeller, and the edge that meets the water first. If it is rotating like this, this is the edge that is meeting the water first. So, that is called the leading edge of the propeller, and the other one is the trailing edge, right. This edge trails the propeller. Am I clear? This, the farthest point of the propeller blade is called the propeller tip, and the one that joins the propeller blade to the boss is called the root. So, I got the root, the tip, the leading edge, the trailing edge, the face and the back. This would more or less define all the main features of a propeller and number of blades, of course, along with RPM and torque it is supposed to observe. What we haven't defined yet is section shapes and the outline of the propeller blade. Now, we will see how they can be defined. Showing you in the form of a diagram. Can you see this? Is it visible to you? Yes? Clearly visible? Right. So, this is the shaft where this shaft is rotating in the clockwise direction looking from this side, and this is the face, this is the back, leading edge, trailing edge. This is the boss, this is the tip, and this is the root where the propeller joins the boss. Is that clear? Okay. Now, let us look at some of the features of the propeller blade. Now, you see here, is this visible? Clear, or should I draw it? Okay. So, if the propeller axis is perpendicular to the shaft center line, this is the propeller center line, propeller axis as it is called, the shaft center line on which the propeller sits is called the propeller axis. If the propeller blade, as in this case, if the propeller blade is perpendicular to it in this plane, if it is perpendicular like this, then this is called a propeller with no rake. But sometimes it may be necessary to rake the propeller or tilt the propeller blade to one side of the plane perpendicular to the propeller axis, like it is shown in the next diagram, this diagram. Can you see it? Is it understandable? Can you understand? Right. What benefit do we get if I rake the propeller? You can see this distance between the propeller tip and the hull here is less than the distance between the propeller tip and the hull here. We know that propeller works in a velocity field which is varying, and therefore it is possible that propeller may transmit pulsating pressure forces onto the ship hull, which may cause vibration in this overhang portion of the hull, that is the stern, which may be transmitted to accommodation and other areas. One way to reduce the effects of this vibration is to increase the clearance between the propeller tip and the hull. This minimum distance, as I have discussed earlier, is given by classification societies. So, if you do not get adequate clearance here, raking the propeller is one way so that we can increase the clearance between the hull and the propeller. Okay. Next we have what is called skew of a propeller. Normally propellers do not have forward rake. Normally they do not have forward rake, but you can always have a forward rake. It is not denied, but it is generally not there, because if you give a forward rake, the clearances reduce the way the propeller is fitted behind the ship. Skew is, if I take the propeller axis like this and if it is perpendicular to this, it is called no skew. So, there is another way to define this. This is the propeller boss. I have got a blade here. Now, at each section, if I draw a radial section, radius here, and this is my section, I draw the midline here, midpoint. If I join the midpoints of all sections like this, all radial sections with this as center, and I find they lie in one line, which is perpendicular to the center like this, then this is called a propeller with no skew. But if I have this blade shifted like this, where the center point gets shifted to this, then this axis, the propeller's vertical axis, is tilted to one side, then it is called skew. Now, some of these diagrams, this diagram shows you various types of skew that exist. This is a propeller blade with no skew, this is a propeller blade with slight skew, and this is a propeller blade which is called heavily skewed, that is, skew is very high. And you can see the center line of each blade plotted here, and the measure of the skew is generally the angle between the propeller non-skewed axis to the line joining the propeller center with the tip, that line. This is the skew line, and the measure is up to the tip, the skew at the tip, that angle. Is that clear? So, this is normally how propeller rake and skew are designed. Why is propeller blade skewed? There should be some reason why we do this heavily skewed propellers particularly. One can appreciate that moderately skewed propellers can be designed to suit the geometry and other constraints. But why heavily skewed propellers? It has been found that heavily skewed propellers can adapt themselves to varied wake field or varied velocity field much better than normal propellers. So, therefore, these propellers have been advocated and have been fitted to a number of ships where the velocity field is very uneven, which might have caused vibration.
Between rake and this skew also increases the gap in both the ways.
Skew may increase gap, but may not, because skew is actually in this plane. So, when the propeller blade rotates, at some place the gap may reduce, some place it may increase. But of course, a well designed, a well skewed propeller may actually improve the gap. Now, let us look at this propeller geometry is actually very interesting. It is a highly three-dimensional geometry, the face, and the propeller face forms a part of what is called a helicoidal surface. Now, what is a helicoidal surface? We already mentioned that it forms a part of the screw surface. If I have an axis here like this, and I have a line here perpendicular to the axis, and I rotate this line here, then the tip of this line will form a circle. But if along with rotating I also give a forward speed to this line, that is, I not only rotate at a constant speed, but I also move this along this axis. So, how will it form? It will go like this. Now, the line that is formed by the tip is a 3-dimensional curve known as a helix. The 3-dimensional curve is known as a helix. Now, if this entire line I trace, it will form a 3-dimensional surface which is called a helicoidal surface. Is that okay? So, here what we have shown is this diagram. If you look at this diagram, can you see? Is that clear? This is a cylinder of a constant radius r, and on top of this I have tried to move this r at a constant speed along the cylinder. It will move along on the cylinder surface, isn't it, because r is constant. So, this is the line A will trace a line like this, a 3-dimensional line up to A1. It's shown in a plane, but it's actually a 3-dimensional curve. This line actually goes like this. Okay. Now, there are two planes we have defined here. One is the perpendicular plane to the in one direction, one perpendicular plane to the propeller axis, which is called the theta equal to 0 axis, and another one normal to the both these the propeller axis as well as this plane, which we have called as z axis. Why I have done this? Normally we know Cartesian coordinate system. In Cartesian coordinate system, we define the position of a point by x, y, z coordinates in 3 dimensions. Is that right? In space, if I define an axis system x, y and z, then any point here will be defined by x, y, z, right? X is the distance this way, y is the distance this way, z is the height from this plane, how far it is. Now, in propellers, since it is connected with a cylindrical movement, it is easier for us to define the propeller point, a point on the propeller blade in what is called cylindrical coordinates. This is Cartesian coordinates. That is r, theta and z. This z remains same as the Cartesian coordinates, but r and theta, that is, if I have got this propeller, let's compare this with this diagram that we have seen. This is the propeller blade. Yeah, this is the propeller blade, and a point here, if I move it, will form a helix, this line, right? This plane is the theta equal to 0 plane, this plane. That means, if I take a radius r, I take a radius r here, if this plane is defining theta equal to 0, then the point passing through that circle that I have drawn would be theta equal to 0, but any other point here will have moved through an angle theta. Am I clear, Mr. Mukherjee? Okay. So, this point can be defined by r and theta, but it has also a coordinate in this direction, that I am calling z. If I pass a plane here as z equal to 0, then the point from that plane to this point will be the z point. So, this point will have a r coordinate, will have a theta coordinate, which is how much it has moved angularly from this axis, and the z coordinate, that from standard plane how far it has gone, how far deep it is, how deep it is. Is that clear? So, any point in space can be defined by 3 coordinates. In Cartesian coordinates, we had x, y, z, where all the 3 coordinates are measured linearly from the 3 defined axes. In the cylindrical coordinate system, we are defining by a point by r, theta and z. So, r and theta define a point in a plane perpendicular to the propeller axis. R is this distance and theta is the angle, and z is the distance from that plane. Okay. So, that defines the coordinates of a propeller. So, that is what is shown here. The axis theta equal to 0 and z equal to 0 are shown. So, any point on this can be. Now, you see this is the face of the propeller blade, this propeller blade. This is the face corresponding to the diagram we had seen earlier. This helix forms a part of that face, or rather the face forms a part of this helix that has been shown here. This part of the curve. Now, if I open this cylinder up, I have drawn this line on the cylinder, now I open it up. What do I get? You see here, this is a cylinder of radius r. So, if I open it up, it will open up to 2 pi r, right? And the distance here along this axis, if it has moved through a distance called pitch, right? I have not defined pitch earlier. That is when this line moved through one revolution, the distance it has travelled longitudinally or axially is called the pitch of the helix or helicoidal surface if the entire surface is moving the same distance. Okay. So, when I open this cylinder up, what do I get? This side will be p and this side will be 2 pi r. This is what is shown here. P is one side will be distance p, the other side will be distance 2 pi r. And this helix will convert itself to a diagonal. It started from one end and ended at the other end. Do you understand? So, this A1 that we had here is converting itself when I open up the cylinder into a diagonal of the rectangle, the two sides of which are p and 2 pi r. Yeah. Okay. Now, this section that was here, this helix that was here on this face section that was here, that will now appear here on this diagonal. Correct? Now, this section that you have seen, this side is the face and this side is the back. Now, I said that the face is a part of a helicoidal surface, or at a particular radius it is a part of a helix. What is shown here is the helix, but you will notice that if I expand this, this is the diagonal going and my section shown here is something like this. It is not actually, the face is not actually on this line, there are little bits of deviations from here, right, and this is the back, this is the face, isn't it? So, this is what is shown here. I have just expanded this. You see here, the face is more or less falling on this helicoidal line, just slightly adjusted, slightly offset at the leading edge and the trailing edge. This is the leading edge L and this is the trailing edge T. The projections of L and T on the exact line is shown here as L dash and T dash. Okay. So, this is the actual section shape of the blade at that radius r. Am I clear? Okay. Now, if this is projected in other views, they will look like this. I think we can skip it for the time being and proceed further. Any doubt so far regarding how a propeller should behave? No, it will not be a flat face. Of course, it is a curved face. This is what I have shown here. This is curved. This is curved. This is face. This is supposed to be on the helicoidal surface, and this you can see is not strictly on the helicoidal surface, but it is slightly offset from the helix at the ends, that is at the leading edge and the trailing edge. Back is not on a helicoidal surface. We are not saying that same thing for the back. We are more concerned about the face, but it is more or less on a helicoidal surface. This is what we are trying to say. So, if the propeller actually moved as a helicoidal surface in a solid medium, please understand, if it moves in a solid medium, then there will be no slip. When you move the propeller forcibly, like a nut moves on a screw of a bolt, it does not have any facility to slip away unless the screw has broken. The nut will move. When you move it one rotation, it will move a certain fixed distance. If you move it 10 times, it will move 10 times of that distance. That distance which it moves in one rotation is called the pitch, and this is what we define pitch here. But since the propeller is moving in a fluid medium, it may not behave as if it is moving in a solid medium. Therefore, there may be slip. Its actual movement may not be equal to P. If I define P as pitch, that is the distance moved in one revolution of this helicoidal surface, the propeller actually need not move P, it may move less because it is in a fluid medium, it may slip. This part we will see later. Right now, let us just understand that though we are defining the propeller blade as a helicoidal surface and defining P as a distance moved in one revolution, in the actual case propeller may not move distance P in one revolution because the medium is not solid. There will be many other reasons, but one of the main reasons is it is not solid. To overcome the resistance in a solid medium, we are actually applying manual force to move it. In a solid fluid medium, what happens as we go along the course, we will see. Have I been clear? Yeah. So, most difficult part of propeller geometry is representing it diagrammatically, showing its various features. So, if I bring back this diagram again, this section that is shown here, this section is what is called an expanded section. That is, if I expand the helix, this is how the section would look. Remember, what I have actually done is, I have taken of this propeller at a constant radius. A constant radius is not a flat line, it is a constant radius. The section shape, what I have shown here, is not a straight line, it is at a constant r. What I have shown here is if that radial arc was made into a straight line, how this section would look. Do you understand? We expanded this to a straight line, isn't it? The helix. This is a diagonal, it is a straight line. So, this is as if we have expanded it along this line, and the angle of this line is phi or pitch angle. You see this angle here, phi, can you see? This angle is called the pitch angle, defined by the P and 2 pi r. And what is pitch angle? You can tell me. Tan phi is equal to P by 2 pi r. P divided by 2 pi r is the tan phi. So, pitch angle phi is tan inverse of P by 2 pi r, right. So, here you have got this line which would come on the helix if it was drawn in a straight line at an angle to the 2 pi r line phi, and this would be as if the section has been straightened.
So that is not the section of that part where it is cutting.
Yeah, it is exactly that. It is exactly that. If I take r here and cut it here, if I take this r and cut it here, this is actually a section in 3 dimensions. But if I have expanded it, pulled it out along the helix, then it becomes a straight line. The section elongates in length along that line. Do you understand? So that is that section. It would look like this, and this is the actual section with which we will be dealing. This is called an expanded section. You got it? Expanded section. Am I clear? Has it been understood? Actually, it is on a 3-dimensional plane. The section is in 3 dimensions. It's as if I have pulled it out to a straight line, and that straight line is at an angle to horizontal. Then that section will look like this. Now, what I do is, I now move it at that same distance r, I make that line horizontal. Instead of diagonal like this, I make this line like this, horizontal. Okay, I made this line horizontal, just physically moved it. Then I get a line. You see here, can you see this diagram clearly? All of you can see it. This is that angle phi. This is the angle phi. Here is what I have, r theta l and r theta t. I don't know whether I have explained this to you or not. This distance here is called r theta l. You see, this distance is actually how I would have seen it on the arc, right? That is a projection. This distance is the projection into this plane, in theta equal to 0 plane. Projection is from here to here. Tell me if you are not understanding. It is very important for us to define the 3 areas that are important to proceed with later on. Okay. What have we done? We have expanded the cylinder. This is P, this is 2 pi r, right? The cylinder was like this. In this, it was like this. I have expanded it, right? This is the helix that I had, right? So far so good. Now, when I expanded the helix, since at a particular radius of the propeller blade, the face I am saying is a part of the helix, that would come as a straight line here. Actually, it is not straight. It will come as a straight line. So, let us say the pitch was coming here, face was coming here. Now, I am not giving any offset to the face. Let us understand the geometry first. And it has a back like this. Let us say this is my blade section. Clear? But if I look at the propeller blade straight away like this, then this would be my point. This is my projected length. My projected length, if I do a projection of the propeller blade, it is here. but if I expand that line, then the propeller blade comes like this, elongated. This can be understood? Okay. Yeah.
That arc will be a two-dimensional curve and that propeller is a three-dimensional curve. So there is a difference there also. You are saying that
We have taken the pitch, no?
a particular
We have taken the pitch here. This is the length of the propeller blade section, actual length.
So you are saying that is at a particular distance r.
Yeah.
Particular arc.
Hmm.
So that arc will be a two-dimensional curve and
This arc is a three-dimensional curve. This is a helix. It's a part of a helix. This arc is also moving. It's part of a helix. You understand? So this is now I have as if I have straightened the helix. So this is a longer length, which I am actually not seeing. What I am seeing is the projection here, this much. So this is actually the projected length of that section, but this is the actual length. If I measure the length, it would be this. What is this? What is this? At constant r, if I measure, I take a thread, put it from here to here at constant r and expand it. This is the length I will get.
That is actual.
Actual length at radius r. Is that clear? So this is phi, and I can say this is theta equal to 0 line. What is the, so this is theta equal to 0 line, let us say, and this is r. So what is the length of this arc? Projected length. Now let us say projection means I will have a circle and a cylinder at a constant section and I draw a line. What is that arc length? R into theta, whatever is the theta. So this distance is therefore r into theta L, and this distance is r into theta T, trailing edge. This is L, this is T. The projections, mind you. Right? Is it too difficult? See here, let us make this surface flat for the time being. What is the section you will see? You will see this length. If I take a photograph, what length I will see? This length, and that will be on this r. So the length of this will be r into theta. Length of an arc is r into theta. All I am saying, from standard coordinates, the leading edge will be r theta L and trailing edge will be r theta T. That is the projection. Okay. So now when I draw the propeller outline, and come back to this diagram. When I draw the propeller outline, if I draw an angle phi here, my section would have come here. That I am drawing on a horizontal plane. Okay. So this is r theta T and this is r theta L. Along that diagonal line at angle phi, and that when I bring it to the horizontal plane, it becomes a longer line. Do you understand? So this section is now known as the expanded section drawn horizontally. Yeah? Have you understood? Huh? I am asking you. You have understood? Okay, good. But if I want to draw a projected line, then it is only on that arc. I put, if I draw at an r, draw theta L and theta T this side, I get this L and theta lines and join them, I will get the projected line. Projection is very simple. Once I know the pitch and once I know the angles theta L and theta T, I can easily draw the projected outline. The expanded outline I have to draw by drawing this phi line, the pitch, and then projecting it onto a horizontal line. That would give me an outline which is called the expanded outline. Okay. So, we have got expanded outline, we have got the projected outline. Now, there is an outline called the developed outline. That is, you see what we are getting the projected outline is, if I had R here and I drew it, if I took the photograph here, how that line would look, that is this circle T, C and L, isn't it? That is how I am drawing the projected outline. Now, suppose I do not actually make it into a straight line, but bring this circle to a single plane. This circle is in 3 dimensions. If I bring this out to 2 dimensions, then I will again get a line which is more than the projected line. Can you understand? That line is called the developed line, where that will be horizontally projected from L and T to give, here in this case we have done L dash and T dash, which is the along with the offset of the leading edge. This is a horizontal line, and it would come on another circle which will be geometrically defined as, if you take p by 2 pi this side and angle phi here, you will get this center, and from there you draw a circle which will automatically give this L dash and T dash projected horizontally on this circle to L double dash and T double dash. If you join them, they are called developed outline. Have you understood? Basically what I have done, if I take at radius R a section, if I draw it projected, same section, I get projected outline. If that section I bring to a single plane by expanding it, not by making horizontal, but in that same circle, then I get developed outline. That circular line, if I pull it and make it straight, then I get expanded outline. Actually, expanded outline is not opening the second curvature. Well, yes, that is true, in 2 different planes, right. Okay. We will stop now, have a small gap and start again. Thank you. Okay, we will continue with propeller geometry. We have seen there are 3 outlines that can define a propeller: the expanded outline, the developed outline and the projected outline. Correspondingly, there are 3 areas that we can define, that is expanded area, developed area and projected area. Now, the area that is covered by the circle with radius r, that is propeller radius, r is the radius up to the propeller tip, that is called the disk area, A0, which is equal to pi r square or pi d square by 4 if d is the propeller diameter. Expanded area is normally represented by AE, developed area AD and projected area AP. So, non-dimensionalizing this, we have 3 area ratios, that is expanded area ratio, which is equal to AE by A0. Similarly, developed area ratio is equal to AD by A0 and projected area ratio, which is equal to AP by A0. So, this is the definition of area. Propeller diameter is given by D and propeller pitch, as we have seen, is given by P. Now, this pitch will be constant at all radii if the propeller face formed a single helicoidal surface, but sometimes we may not give a constant pitch across the radius, that is, the pitch may vary. Like if this is the radius r, this is full radius, then your pitch distribution may be constant. If it is a constant pitch, then the pitch distribution will be like this to the r. This is the pitch. At all radii the pitch is constant. On the other hand, I may decide that this pitch distribution is not okay, I can reduce pitch at the root and increase pitch at the tip. So, in that case I can also give a pitch distribution which may look like this. I can give a variable pitch distribution to the propeller blade. In that case, what will be the resultant pitch? If I give a variable pitch distribution, the resultant pitch of the propeller, if I want to designate it by a single quantity, then in the variable pitch case, resultant pitch you can see can be given as, mind you, the pitch is starting only after the root, the boss. The blade is starting from the root till the tip, right. Shape is known as aerofoil section, where you can see the leading edge is not really sharp, it is rounded, and the trailing edge is sharp. That is how propeller blades are made. The leading edge has a curvature, but the trailing edge is sharp. That is another way of knowing which is the leading edge. The one that is sharp is the trailing edge, the one that is blunt is the leading edge, and that is the one that will be meeting the water first. So, you can also decide which way the propeller rotates by just looking at the propeller, if it has the aerofoil section. Now, as we have seen earlier, you can also give some offset to the face from the straight line, and still it would be a aerofoil section. This is the most commonly used section for majority of propellers available in the world. This, on the other hand, is called a segmental section, where the back of the propeller section is a part of a circle. Unlike an aerofoil section, you can see it is not part of a circle, it is blunt forward and sharp towards the trailing edge. Here in segmental section, the back is part of a circle. This is many times used where there is a requirement of typically these sections are used in propellers for trawlers, where you require not only free running speed, but also some amount of pull that one must exert, such as hauling a trawl net or something like that. In many propellers, there is a combination of both aerofoil section and segmental section. That is, aerofoil sections up to a certain radius, and then the sections slowly change to segmental sections. We will see some of these propellers later on. Then what you have is called a lenticular section, where the section is symmetrical about its center line. There will be a drag in the same direction, but a lift in the opposite perpendicular direction. So, if you look at this lift which is going like this, most of its component is in the axial direction. If I now compute it, one in this direction, one is this direction, most of it is this way, because the perpendicular is making a very small angle to the axis of the propeller.
Does it mean that the thrust and the lift are acting in the same direction?
Thrust and lift are not different. The axial component of lift is the thrust. Otherwise, what is thrust? How do you get this axial force? This lift that I am getting, the component of that in the axial direction is what I call an element of thrust by any point here. That thrust integrated over the whole blades, all blades, gives me the total thrust on the propeller. Is that clear? I am also losing something in the form of drag. So ultimately, the propeller efficiency will be a ratio between lift and drag. But have you understood how lift is being generated? Yeah. So let us look at this diagram a little bit. We also know from aerofoil theory that if you go on increasing this angle alpha, called the angle of attack, if I go on increasing this angle of attack, lift increases more or less linearly like this, as is shown here. That is, I get small lift if the angle is small, and if my velocity angle of attack is more and more, I get more and more lift. But very strangely, beyond a certain lift angle, certain angle of attack, this is angle of attack axis, lift suddenly falls. That means you do not get any more lift. Okay? This is called the stall angle. Okay? It is called the stall angle. So we have to design your propeller that the lift is, the angle of attack is within this. Now when you go reducing the angle, when it is at a particular angle to the propeller, there will be no lift. So that angle is somewhat this is called the no lift angle. Only when the angle is created with respect to that, start getting lift till stall angle. So our aim should be to design the blade sections so that you stay between no lift line and stall angle. Am I clear? Okay, we will stop here and next class we will continue with propeller theories. Thank you.